I want you to step into a very specific kind of room for a second. Picture the absolute highest floor of a glass and steel skyscraper in Frankfurt, or maybe Chicago.
Right, the classic corporate fortress.
Exactly. It's a corporate boardroom, climate controlled to a perfect, 70 degrees. It is completely silent.
Yeah.
And taking up the entirety of the main wall is this pristine, probably $50 million corporate digital dashboard. It's just glowing with metrics.
Uptime percentages, throughput graphs, just endless rows of green check marks.
Yes. And if you're an executive sitting in that leather chair, you are looking at the ultimate picture of control. Your empire is functioning perfectly.
On a screen, at least.
Right, on a screen. Now, I want you to take that sanitized, glowing image, hold it in your mind, and just slam it violently into the physical reality of a factory floor in Stuttgart or Detroit.
Oh, wow. Yeah, that is a jarring transition.
It is. The air down there is thick with, aerosolized machine coolant. The noise is just this deafening, rhythmic, mechanical pounding.
It's a brutal environment.
And right at this very second, a $2 million heavy cast-iron multi-axis robot is violently slamming its tooling into a hardened steel fixture.
Sparks raining down, the safety interlocks trip, the whole line just dies.
Exactly. The entire production line grinds to a halt, and thousands of dollars are evaporating by the minute. And the reason this catastrophic failure happened...
That's the crazy part.
Because the room temperature on the factory floor rose 12 degrees since morning, and the massive metal frame of that robot physically expanded.
Yeah. And that contrast right there between those two rooms, that represents a $1 trillion blind spot in global manufacturing today.
$1 trillion. That is just a staggering corporate failure.
It really is, because you have the map in the boardroom, which is this beautifully designed static digital fiction, and then you have the uncompromising territory of the factory floor, which is governed entirely by, thermodynamics and friction.
Right, the map is basically lying to you about the territory.
Exactly. The problem corporations are facing is that they trust the map more than the physical reality.
Well, we are going to dismantle that lie today. Welcome to the Deep Dive.
Glad to be here.
We are unpacking what I would honestly call a masterclass in first principles thinking and just absolute industrial minimalism.
Yeah, it's a fascinating shift in how we approach these massive physical problems.
We've got an incredible stack of sources guiding us today, too. We're looking at the unvarnished operational blueprints from deep tech analyst Prasad Bond.
Really eye-opening stuff in there.
Plus the 2026 industrial AI predictions from AMD machines, and this massive comprehensive data intelligence report detailing exactly how edge AI is being used right now.
It's a really unique combination of materials. Because, we're bridging high-level corporate strategy with the absolute granular mechanics of hot metal and grinding gears.
Yeah, we're getting our hands dirty today.
We are moving away from abstract theories of how automation, should work, and looking at the brutal physics of what actually happens when machines inevitably degrade.
Right. Because if you were tasked with pitching a solution to this trillion-dollar failure to the executives sitting in that boardroom, you couldn't hand them a dense spreadsheet.
No, their eyes would glaze over instantly.
As an ad creative guy, I look at this and think, you have to approach it like a viral, culture-hacking ad campaign. You target these high-net-worth industrialists with a stark, undeniable image of a broken machine.
You have to break through the dashboard illusion.
Exactly. And then you offer them a guilt-free, ultra-minimalist solution to their most expensive headache. Acknowledge the physical reality, ditch the bloated software, and basically apply Dieter Rams' design philosophy to factory automation.
Less but better.
Yes, less but better applied to grease and steel. So let's start with section 1, the corporate hallucination versus physical reality.
The hallucination is really the root of the issue here. Prasad Bond highlights this as a shared global fiction.
What do you mean by shared fiction?
Well, when an executive or even a software engineer looks at a computer numerical control machine, a CNC machine, they operate under this assumption that a coordinate entered on a screen remains an absolute, unchanging truth forever.
I see. So if the code says, move exactly 10.5 millimeters to the left, they assume it's going to do exactly that today, tomorrow, and 6 months from now.
Right, which completely ignores the basic laws of physics. The hallucination relies on the belief that because software operates in a static, perfect digital universe, the hardware it controls must also exist in that static universe.
But hardware exists in reality. And reality is messy.
Exactly. Hardware operates in a degrading reality. If we look at the physics of failure on a factory floor, we are dealing with high-speed spindles rotating at like 30,000 revolutions per minute.
It's generating a massive amount of heat, right?
Unbelievable amounts of heat. And when you heat up cast iron and brushed steel, the atomic structure becomes more energetic and the metal literally, physically expands.
Just from running its normal cycle.
Yes. Plus, you have servo motors running non-stop. The internal bearings begin to wear down by micrometers. The heavy industrial grease designed to reduce friction thins out under that continuous thermal load.
Wow.
And the violent, continuous vibration of cutting metal slowly alters the structural geometry of the machine's frame over time.
So over a 6-month production run in, say, a Tier 1 facility, the absolute 0 point, the true mathematical center of that machine, is physically drifting away from where it started.
Yes. The industry refers to this as calibration drift, and it functions as this silent, devastating tax on manufacturing.
But doesn't the machine know it's drifting?
That's the fatal flaw.
Yeah.
The machine controller, the software brain dictating the movements, is completely blind to its own physical state.
Wait, really? It has no idea.
None. It has no sensory input telling it that its internal gears are worn down by a fraction of a millimeter, or that the ambient temperature has expanded its arm.
So it just assumes it's physically identical to the day it was assembled on the showroom floor.
Precisely. It continues sending the cutting tool to what it mathematically calculates is the correct coordinate. But in physical reality, the tool is now cutting off center.
So if the machine isn't fixing itself, a human being has to step in and absorb that mechanical failure.
Yeah, the floor operators have to act as human shock absorbers. Bond's blueprint details this incredibly vivid, frustrating scenario to illustrate this.
Okay, set the scene for me.
It's late on a Friday night. A maintenance technician is inspecting a finished part and notices a 14-micron tolerance deviation.
Now the machine is drifting, producing defective parts.
Right. Now, the technician doesn't redesign the system. They halt the line, pull out a battered clipboard covered in grease, and manually type arbitrary offset numbers into the CNC keypad.
They're just guessing.
Pretty much. They are manually guessing how much the metal has bent, typing in a countermeasure, and just begging the machine to cut straight for one more shift.
That is insane. That is
Yeah.
completely undocumented, exhausting labor. The human operator is basically reduced to a manual feedback loop for a degrading piece of metal.
Exactly. They guess the physical sag, they punch in a software offset, they cross their fingers, and they hit cycle start.
And I'm guessing they have to do this constantly.
They repeat this ritual weekly, sometimes multiple times a shift. They keep doing it until the machine becomes so mechanically compromised that a catastrophic collision occurs.
Like the spindle crashing into a titanium workpiece.
Yeah, the tooling shatters, and production stops entirely for a weekend-long recalibration marathon.
I'm trying to think of how this translates to an everyday experience for, someone not on a factory floor.
It's a tough dynamic to grasp if you haven't lived it.
It feels like, it's like driving a car cross-country, and over a 6-month road trip, the steering wheel slowly disconnects from the steering column.
Okay, yeah, that's a good analogy.
But instead of pulling over to a mechanic and fixing the linkage, your manager just tells you to steer a little harder to the left every single day.
Yes, you are physically compensating for the broken mechanics.
Right. You're sitting there, white-knuckling the wheel, absorbing the failure with your own exhaustion, until eventually the math fails and you drive into a ditch.
And if you're listening to this right now and you work in a corporate office, you almost certainly have a digital equivalent to this.
Oh, absolutely. That one massive bloated spreadsheet, you have to manually update and reformat at 5 p.m. every Friday because the automated enterprise software is broken.
Exactly. You are acting as the manual feedback loop. You are the human shock absorber for a flawed system.
So how does corporate leadership usually respond to this? When yield drops and downtime spikes?
Well, this is where the hallucination gets incredibly expensive. Executives rarely investigate the thermal dynamics of the factory floor.
Because they're up in the boardroom looking at the screen.
Right. So they purchase massive, abstract enterprise software suites. They hire consulting firms to conduct long-term audits. They install more digital dashboards to monitor the downtime.
So they're essentially spending $50 million to buy a higher resolution screen to watch the car drive into the ditch.
That is exactly what they are doing. Or worse, they blame the driver. They point to the floor worker and ask why they couldn't hold the required tolerance.
Which is incredibly unfair.
It is. If manual compensation by an exhausted technician is the disease, Injecting $50 million of cloud-based enterprise software into the facility is the wrong cure.
Because it just adds more abstraction.
Right. It merely adds more abstract digital nodes on top of a brutal physical reality. The software is the map. The metal is the territory. The map is static, but the territory is constantly shifting.
So to solve this, the software must be forced to continuously read the territory. We need a minimalist, hardware-first intervention.
Yes.
Stop tracking the broken machines with a dashboard and let the machine track its own decay, which transitions us right into Section 2. First principles and the Dieter Rams approach to robotics.
This is where the solution gets really elegant.
How do you resolve a $1 million operational bottleneck? I love this. Use a $50 sensor and absolute minimalism.
The proposed solution is just a masterclass in parameter engineering. It is visually and functionally shocking in its simplicity.
Tell me how it works.
You bypass the enterprise software entirely. You procure a $50 edge AI vision sensor, like a commercially available industrial camera, or a basic laser displacement sensor.
Okay, a $50 sensor.
And you physically bolt it directly to the cast iron frame of the machine.
See, I am captivated by the visual aesthetic of this solution as an ad creative. It's very stark. Picture a massive, heavy metal phonic robot arm, right? It's intimidating industrial brutalism. And bolted right onto the spindle housing is this tiny, matchbox-sized matte black sensor.
Emitting a single red laser diode.
Yes. No glowing cyberpunk effects, no complex touchscreens, just a single piece of geometric precision intersecting with the unvarnished metal. It embodies Dieter Rams.
It absolutely strips away everything that does not contribute to the essential function. Form follows function in the purest sense.
So what's the software running this? It can't be a massive enterprise suite.
No, the minimalist software driving this is equally stripped down. You do not deploy a massive team of software engineers. You write 12 lines of Python code.
12 lines.
That's it. The logic operates on a 200 millisecond loop. Manufacturing processes naturally include brief pauses, right? Like during a tool change.
Okay, so the machine pauses for a second.
During that fraction of a second, the machine positions the sensor over a fixed physical datum block bolted to the table. The red laser pings the block.
Wait, okay, hold on. How does a single red dot tell a $2 million machine that it is broken? Are we talking about measuring the time it takes for light to bounce back?
No, it's actually simpler than that. It uses optical triangulation.
Okay, break that down for me.
It's a beautifully simple geometric principle. The sensor emits the laser at a specific angle, and the light hits the datum block. The camera lens inside the sensor looks at where that red dot appears on its internal image sensor.
Oh, I see. Because the geometry of the triangle between the laser, the block, and the camera is fixed.
Exactly. Any physical shift in the machine changes where the red dot hits the camera sensor. The Edge AI module runs a local calculation.
Comparing where it sees the block versus where the map says it should be.
Right. The mathematics are instantaneous and absolute. It calculates the exact thermal drift or mechanical sag down to the micrometer.
And then what?
If that drift exceeds a predefined threshold, the module pushes a micro offset directly into the machine's controller.
So an API call, an application programming interface call. It's essentially the sensor passing a secure digital note directly to the machine's brain, bypassing the main factory server entirely.
A perfect description. It is a localized digital handshake. The sensor just tells the controller, you are currently 0.05 millimeters off-center, adjust your coordinates.
And this entire process, from the laser pinging the block to the machine adjusting its internal map, happens in 200 milliseconds.
Before the operator even takes a breath, the machine has healed its own coordinates.
That is wild. The physical hardware is still flawed, the metal is still expanded, the gears are still worn, but the minimalist software has compensated based on real-time physics.
The machine is learning its own decay.
But I have to push back here. I am putting on my executive hat for a second.
Go for it.
If the solution to calibration drift, this massive, expensive blind spot, is truly just 12 lines of Python and a $50 camera I can buy online, executives are right to be skeptical.
Why do you say that?
Because a $50 consumer webcam is not going to survive inside a 110-degree stamping press environment covered in cutting fluid. It will vibrate to pieces in an hour. Why isn't every factory doing this if it's so simple?
Well, Well, the skepticism regarding the hardware would be valid if we were talking about consumer electronics, but we are deploying industrial hardened edge components
Is that built differently?
completely differently. These sensors are solid state, they have zero moving parts. The internal electronics are potted, which means they're encased in hard resin, so vibration cannot shake the solder joints loose. Ah, okay. So the fluid and heat aren't an issue.
Right, they are sealed against cutting fluids and thermal shock. The physical durability of the sensor is a solved engineering problem.
Then what's the holdup?
The resistance from the C-suite does not stem from hardware fragility. It stems from a systemic, almost dogmatic addiction to centralized control, specifically the delusion of the cloud.
The cloud. Right. Because corporate structures are designed to funnel all data to a centralized server to populate those boardroom dashboards.
Exactly. To scale this DRAM-style fix, you must sever the cord to the server room. The data has to be processed locally.
Which introduces a massive hurdle. Because if you are a plant manager trying to implement this, how do you navigate the corporate IT bureaucracy?
IT is historically very protective of the network.
Right. The IT department is not going to let you bolt an unauthorized sensor onto a machine and plug it into their network.
No, they won't, which is why the blueprint outlines a strategy called the 48-hour protocol. It is designed to completely bypass bureaucratic inertia.
I love a good protocol. How does it work? The protocol dictates that you do not request a committee approval. You do not schedule cross-departmental alignment meetings.
You just go rogue.
Essentially, yes. You isolate the specific variable causing the bottleneck. You acquire a commercially available edge computing module. You attach the sensor to the most stubborn, drifting CNC machine on your floor.
And then write the Python script.
Yes, write your script. And over the weekend, you do not connect it to the machine's controller. You run a silent test.
Oh, I see. You just log the data. Every hour, the laser pings the block, and the edge module records the exact physical drift into a raw text file.
Right, a CSV file, just comma-separated values, the most basic spreadsheet format in existence.
So by Monday morning, you have a raw, irrefutable data file.
You take that file and slide it across the plant manager's desk. You demonstrate, with hard localized data, that the machine's internal software map has completely detached from the physical reality of the territory.
You use the data to prove the existence and scale of the bottleneck.
Once the hypothesis is proven offline, you flip the switch, engage the API write access, and the machine begins auto-calibrating.
It is a total culture hack. You are using undeniable physical evidence to force a change in software strategy.
It works because the data is undeniable.
But to understand why this localized approach was historically impossible and why it's suddenly viable now, we have to look at the massive shift happening in the industry.
Section 3, Edge AI versus the cloud delusion.
Right. According to the AMD Machines 2026 predictions and the Data Intelligence Report, the landscape is violently pivoting. Edge AI is becoming the default architecture for time-critical manufacturing.
The era of the cloud solving everything on the factory floor is ending.
Why now? What's the fundamental limitation of the cloud?
The limitation is dictated by physics, specifically the speed of light and network routing. For the past decade, industrial AI deployments were heavily cloud-dependent.
Meaning everything had to be sent out of the building.
Right. The architecture required gathering data from a machine, transmitting it over a network to a cloud server hundreds of miles away, waiting for the server to process the inference model, and transmitting a command back down to the machine.
I am just imagining a manager sitting in an office in New York trying to micromanage a line worker in a factory in Texas over a degraded cellular connection.
That's a great way to picture it.
Move your hand left. No, wait, right. Hold on. The connection dropped. It is an absurd way to manage a physical process.
Completely absurd. Now, sending data to the cloud is perfectly acceptable for analytics dashboards that operate on hourly or daily cycles.
If an executive just wants to review the total part count from yesterday, the cloud is fine.
Yes, it's sufficient for that, but it fundamentally fails for real-time process control. In modern manufacturing, millisecond latency is not a preference. It is a physical mandate.
Give me an example of why that speed is so critical.
If a production line is stamping 200 parts per minute and you rely on a cloud round trip to detect a visual defect, the latency might be half a second.
And in half a second, the machine has already stamped multiple parts.
Exactly. By the time the server analyzes the image and tells the machine to halt, 50 defective parts have already moved down the line.
You cannot wait for the cloud when the metal is moving. That 200 millisecond auto-calibration loop we discussed earlier is physically impossible if the data has to leave the building.
The intelligence must live on the edge, bolted directly to the frame.
So what's enabling this now, if it wasn't possible a few years ago?
This architectural pivot is entirely driven by rapid advancements in silicon. The reports document that dedicated industrial AI processors are now shipping in massive volumes.
What kind of processors are we talking about?
We are seeing platforms like NVIDIA's Jetson Orin, Intel's Meteor Lake industrial chips, and specialized processors from Qualcomm.
And these aren't just like the chips in my iPhone.
No, these are not fragile smartphone chips. They are hardened compute modules designed to run complex AI inference models directly at the machine level with sub-10 millisecond latency.
A lot of the documentation mentions TPUs, right? Tensor processing units.
Yes, TPUs are a major factor.
My understanding is that a TPU is a microchip specifically designed and optimized to do nothing but run artificial intelligence mathematics incredibly fast, right there on the local hardware, without needing a massive power supply. Is that right?
That is correct. They process neural networks exponentially faster than traditional CPUs, and this localized compute power solves another massive problem: the data reality problem.
The sheer volume of data, you mean?
Yes, modern factories generate an incomprehensible volume of industrial IoT data. High-resolution video feeds checking for defects, continuous acoustic signatures listening for grinding gears, high-frequency vibration metrics.
What's terabytes of data?
Easily. If an IT department attempts to transmit all of that raw data to the cloud, the bandwidth costs alone will bankrupt the operation.
Let alone the security risks.
Exactly. You introduce network packet delays and severe cybersecurity vulnerabilities by transmitting proprietary production telemetry outside the facility's firewall.
So by processing the data locally at the source, the edge module acts as a relentless filter.
Yes, a very smart filter.
It doesn't send a terabyte of raw video to the cloud. It distills the video down to a tiny text string that says, machine drifted 0.05 millimeter, offset applied.
It extracts the actionable insight and instantly discards the heavy raw data. This is what enables line speed decisions.
The AMD machine source cites some pretty remarkable performance metrics on this, actually. Edge-deployed vision systems are achieving 99.7% defect detection rates at cycle times under 0.3 seconds.
They are inspecting over 200 parts per minute without missing a beat.
That's incredible. I guess the ultimate advantage of edge AI becomes apparent during infrastructure failure, right? What occurs when the factory Wi-Fi router fails or the external internet connection drops?
If the factory relies on the cloud, the robots freeze. Production halts immediately because the machines have lost their brains.
But with the localized edge module, the machine is indifferent to the network status.
The intelligence is bolted to its shame. The production line continues running autonomously.
So we are giving the edge AI module the absolute authority to act instantly without requesting permission from the cloud manager.
Which is a huge shift in the power dynamic.
It decentralizes the power completely. Local maintenance teams and process engineers are empowered to apply targeted, localized fixes to physical problems without waiting 3 months for IT to provision cloud resources.
But, when you are pitching this to the C-suite, the decentralization of power isn't enough to win them over.
Right. You have to pitch the financial math. Let's move into section 4, the financial reality of predictive maintenance.
Automation cannot be pitched as a cost center. It must be pitched as undeniable profit growth.
Because there's a lingering myth regarding industrial automation software, right?
Yeah.
That it requires a massive initial capital expenditure with a hazy, multi-year return on investment.
Historically, companies would invest millions in AI platforms and wait years to see a positive return. But the 2026 data indicates that this economic model has entirely collapsed.
Why? What changed the math?
Hardware commoditization. According to the AMD source, the cost of industrial cameras and edge compute modules has dropped 40% since 2023. We are no longer discussing million-dollar infrastructure deployments.
Oh, wow, 40% in just a few years. So that radically compresses the ROI timelines.
Dramatically. Vision-based quality systems that previously required 18 to 24 months to pay for themselves are now achieving a return on investment in 6 to 9 months.
6 to 9 months. That's a no-brainer for an executive.
Especially in high-stakes manufacturing fields, where the cost of a defective product escaping the facility is catastrophic.
Let's talk about those high-stakes fields. The Data Intelligence Report specifically analyzes automotive manufacturing, hunting for microscopic surface defects on paint jobs, electronics manufacturers inspecting the integrity of complex solder joints on circuit boards.
And the medical device industry, which is a perfect example.
Yes, let's spend a moment on the medical device example because I think it crystallizes the value perfectly. Imagine a factory machining titanium casings for pacemakers.
A very precise operation.
A nanometer-level scratch on that casing might seem totally insignificant to the naked eye, but if that scratch goes undetected, it acts as a stress riser.
Exactly. Once implanted inside a human body under constant physiological stress and pressure, that microscopic scratch propagates into a microfracture.
The casing fails, and it's a matter of life and death.
It is. But if an edge AI camera using glancing optical light can catch that nanometer defect in 0.3 seconds,
The system pays for itself instantaneously by preventing a lethal failure and a massive corporate recall.
precisely. But the financial impact extends far beyond just defect detection. The most significant profit driver is actually predictive maintenance.
Right. And the data reveals a stark divide between successful and failed predictive maintenance strategies.
Yes. The corporations that failed were the ones that attempted to bolt AI algorithms onto legacy cloud systems, analyzing spotty historical data.
They were attempting to predict future failures by analyzing a flawed, incomplete past.
Which never works. The corporations that succeeded returned to first principles. They abandoned the historical cloud data entirely.
What did they do instead?
They installed localized sensors directly onto the mechanical stress points, vibration sensors on the chassis, acoustic monitors near the gears, current draw sensors on the power supply.
Just getting right as close to the metal as possible.
By monitoring those specific physical parameters at the edge in real time, facilities are recording 40% to 50% reductions in unplanned downtime.
Let's quantify that financial impact for a second. In a modern Tier 1 facility, a critical CNC machine or a heavy stamping press operates for 20-plus hours a day.
It's the heartbeat of the factory.
When that machine breaks down unexpectedly, the cost is not merely the price of a replacement gear.
No, the facility suffers idle labor costs, disrupted downstream supply chains, and missed delivery penalties.
The cost of unplanned downtime is widely estimated at $5,000 to $15,000 per hour.
It is a phenomenal bleed of cash.
So the strategy is to transform maintenance from a state of reactive panic into a schedule of precise micro-calibrations. I want to understand how this works mechanically. How does a current draw sensor predict a failure?
It's quite elegant. It's monitoring the electrical amperage going into the motor.
Okay.
As an internal bearing begins to degrade, the microscopic friction inside the motor increases. To maintain the same rotational speed against that increased friction, the motor must pull slightly more electrical current.
I get it. So the Edge AI establishes a baseline for normal current draw.
Yes. And when it detects a sustained microscopic increase in amperage, long before a human could hear a grinding noise or feel a vibration, it flags the anomaly.
It is analyzing the invisible microstressors before they become macroscopic failures.
Exactly.
It's less like a mechanic living under your hood and more like how your smartphone's battery management software monitors your charging habits, adjusting the voltage dynamically to prevent the lithium-ion cells from degrading over time.
It intervenes before the damage actually occurs.
Instead of a bearing exploding on a Tuesday afternoon and shutting down the line for 3 days, the Edge AI analyzes the current draw and dictates, this bearing will fail in exactly 72 hours.
You predict the failure 72 hours in advance. The supply chain software automatically orders the replacement part. The maintenance team schedules the repair for a planned shift change on Sunday morning.
You lose 0 hours of productive uptime.
It is, but, while the mechanical and financial benefits are undeniable, there is a profound human element to this equation that corporate leadership frequently ignores.
Let's dive into that. Section 5, restoring dignity, human safety, and the minimalist skills gap.
When we discuss industrial automation, the traditional narrative immediately defaults to robots replacing human workers.
Right, the dystopian view.
But Prasad Bond introduces a concept called restorative engineering.
What does that mean in practice?
Restorative engineering mandates that technology must be utilized to restore human safety, human capability, and human dignity. It represents a profound philosophical shift. True automation is not about replacing the human being. It is about decoupling human labor from mechanical wear.
We have to break the cycle of forcing operators to act as manual feedback loops.
Exactly. When a technician is typing arbitrary offsets into a dirty clipboard at 2 a.m. simply to force a degrading machine to limp through a shift, that is an indignity.
It is undocumented, exhausting, low-value labor.
Restorative engineering dictates. Let the localized sensors manage the metal so the human beings can manage the strategy and the innovation.
If you are listening to this and nodding, You understand the relief of finally automating a soul-crushing manual task. But achieving that restorative state requires addressing the industrial skills gap, doesn't it?
Yes. The AMD predictions highlight that the manufacturing AI skills gap is actively widening. The industry is trapped in a flawed hiring paradigm.
They are obsessively searching for unicorns.
They really are. They want an individual who possesses decades of gritty, tactile factory floor experience as a process engineer, who also happens to hold a PhD in neural network data science.
Those unicorns do not exist. You have universities producing brilliant data scientists who have never smelled cutting fluid or set foot on a factory floor.
Right, and you have veteran manufacturing engineers who intimately understand the thermodynamics of the machines but have never trained a machine learning model.
If a corporation waits to hire the unicorn, their factory will become obsolete.
Exactly. The minimalist solution to this skills gap is to abandon the search for unicorns and empower the domain experts you already employ.
How do you do that without sending them back to school for 4 years?
This necessity is driving a massive industry shift toward low-code and no-code industrial AI platforms. We are seeing rapid adoption of systems like Cognex's Vision Pro Vita or Landing AI's Landing Lens.
So the objective is to provide basic AI literacy to existing process engineers.
Yes. You provide them with a highly visual drag-and-drop interface. They do not need to write complex Python scripts or understand the underlying neural network architecture.
They simply need to show the AI 100 pictures of a physically perfect part and 100 pictures of a defective part, and let the software handle the complex mathematical modeling in the background.
It lowers the barrier to entry, so the people who actually understand the physical manufacturing process can wield the technology.
That technological empowerment extends directly into worker safety too, which is simultaneously the most impactful and the most sensitive application of Edge AI.
The Datum Intelligence Report identifies Edge AI for worker safety as a critical growth sector. The objective is to utilize localized surveillance as proactive protection, rather than corporate punishment.
This is an incredibly thorny issue to navigate. We're talking about utilizing AI cameras to monitor if workers are wearing their required personal protective equipment, their PPE.
Monitoring for physical signs of extreme fatigue, unsafe ergonomic lifting movements, or detecting if a worker inadvertently steps into a restricted zone near a moving robotic arm.
The technological capabilities are profound. I mean, an Edge AI camera can detect if a worker's hand crosses an invisible safety plane near a high-speed stamping press and trigger a millisecond machine halt, preventing a life-altering amputation.
It can analyze the microexpressions and blink rates of a forklift driver to detect extreme fatigue before a fatal collision occurs.
But the technology is only half the challenge. You must rigorously analyze the psychology of factory floor surveillance.
It's the hardest part of the deployment.
Because when corporate management announces AI surveillance for safety, the workers on the floor understandably translate that to, Big Brother is monitoring how many seconds I spend in the restroom.
Of course they do. They feel micromanaged, untrusted, and commodified.
How does an executive pitch this system so it is genuinely received as a protective safety net and not a corporate leash? If you get the messaging wrong, you trigger the crab mentality, where the workforce actively rejects and sabotages the system.
The absolute core of the pitch must be the localized data architecture. Localized, localized, localized.
Explain that distinction.
If the camera system is transmitting video feeds up to a centralized cloud server where corporate HR can arbitrarily audit an employee's movements, it is a leash. That architecture destroys morale and trust.
Right. But if the intelligence is processed entirely on the edge, the psychological paradigm shifts.
Yes. The Edge module does not record video. It does not possess a hard drive to save the data. It is merely scanning the live visual feed for specific safety parameters in real time and discarding the footage instantaneously.
So the alerts remain entirely on the floor.
Exactly. If a worker forgets to put on their safety goggles, the localized system flashes a yellow indicator light at their specific workstation. It does not log a demerit in a centralized HR database. It simply acts as a real-time digital spotter.
It prevents the accident locally and instantly.
When the workforce truly understands that the system is completely blind to everything except their immediate physical safety and that the data never leaves the room, the technology transforms from a panopticon into a protective shield.
We're returning to DRAMs again. Functional clarity, visual reduction. Strip away all the unnecessary invasive corporate tracking and focus the technology entirely on the singular, essential function of physical safety.
It's minimalism applied to human-machine interaction.
Edge AI secures the present moment. It secures the physical machine through automated micro-calibrations, and it secures the physical worker through localized safety nets.
But how do we utilize this pristine, newly localized data to secure the future of the entire manufacturing operation?
That transitions us perfectly to the final horizon of the reports.
Oh, Section 6.
The autonomous horizon, digital twins, and scaled AI.
We have thoroughly examined how to fix individual isolated machines using 12 lines of code. But the 2026 industrial shift is about moving from these isolated pilot programs into full autonomous production environments.
And the strategy involves taking the highly accurate real-time data generated by these edge sensors and feeding it into the evolution of digital twins.
Yes, the digital twin is the ultimate destination for all this edge data.
Now, I have to admit, I struggle with the concept of a digital twin. It has been a corporate buzzword for a decade.
It really has been overused.
In most cases, it just seems like a glorified, highly detailed 3D visualization model of a factory that a CEO puts on a screen during a shareholder presentation. It looks impressive, but it doesn't actually interact with the physical world.
Right, it's just a rendering.
I feel like I'm missing the bridge between a highly detailed video game and the actual factory floor. If a physical gear is wearing down in reality, how does the 3D model on the screen know about it?
Your skepticism regarding the legacy definition of digital twins is entirely justified. But the 2026 generation of digital twins has evolved far beyond visualization.
Who are they now?
We're discussing real-time, predictive, closed-loop, cyber-physical ecosystems, platforms developed by Siemens Accelerator, NVIDIA Omniverse, and Rockwell Automation.
So where's the bridge?
The bridge you are looking for is the edge data. The physical sensors bolted to the machines are constantly streaming live telemetry vibration frequencies, thermal expansion metrics, current draw directly into the physics engine of the simulation.
Oh. So the simulation is not an animation. It is a complex mathematical replica calculating the exact physical state of the factory based on real-time sensory input.
Exactly. It's a living, breathing mathematical mirror of the factory.
And it doesn't just show you what is happening right now. Its physics engine possesses the predictive capability to show you what will happen if you change a variable.
Yes. The AMD report details this incredible scenario to illustrate this. An engineer can virtually swap out a robotic end effector, the physical tool at the end of the robot arm, inside the simulation.
And the digital twin will predict the new cycle time for the entire factory with 98% accuracy, without anyone ever touching the physical robotic cell.
The implications for factory design, commissioning, and continuous optimization are staggering.
Because historically, designing and building a new robotic assembly line involved months of expensive physical trial and error.
Right. It was a nightmare. You bolt the steel together, you program the kinematics, the robot inevitably crashes into a fixture, you weld a new fixture, you reprogram the path. It is a slow, iterative physical process.
Now, with a highly accurate digital twin continuously fed by real edge data, an engineering team can debug the entire factory offline.
They run millions of simulated cycles before a single physical brick is laid or a single motor is powered on.
The reports state they're achieving 30% to 40% reductions in physical commissioning time.
That represents months of saved engineering labor and millions of dollars in conserved capital.
If a digital twin can simulate a complex factory cycle times with 98% accuracy, are we essentially creating a perfect save state for physical manufacturing? Can a plant manager literally hit Command Z on a bad factory layout?
In a virtual environment, yes. The plant manager can model the addition of a second production shift, incorporating the historical speed and fatigue data of different operators.
They can model a sudden supply chain disruption where a specific raw material is delayed.
The digital twin dynamically tunes the parameters of the simulation to predict where resource waste will occur and how throughput will be impacted.
And when you integrate this predictive capability with autonomous material handling, the factory truly comes alive.
Autonomous material handling using Edge AI to power automated guided vehicles, or AGVs, and robotic forklifts, creating a fully automated internal logistics network.
I want to paint a picture of what this ultimate Dieter Rams factory floor looks like.
It's quite a vision.
It is impeccably clean. It is continuously self-optimizing. It is surprisingly quiet, save for the rhythmic hum of machines that are quietly healing their own coordinates in 200-millisecond loops.
You have AGVs navigating autonomously down the aisles, using edge vision to dodge unexpected physical obstacles in real time.
You have the closed-loop system instantly rerouting the flow of heavy materials based on sensor data, completely bypassing the need for a frantic human manager holding a clipboard and a walkie-talkie.
It is the harmonious intersection of pristine digital logic and unyielding physical reality.
By embracing first principles, we are stripping away the complex, reactionary, bloated layers of corporate management software and replacing them with autonomous, localized, highly efficient engineering.
That is the core of it.
Let's bring this deep dive full circle. We began with the culture-hacking premise of a disruptive ad campaign targeting industrial executives.
The boardroom versus the factory floor.
Right. And the core message of that campaign is undeniable. The era of purchasing expensive, abstract, cloud-based software dashboards to monitor broken, degrading physical hardware is over.
It is mathematically and physically unsustainable. You cannot fight the laws of thermodynamics with a cloud-based spreadsheet.
The future of industry belongs to the edge. It belongs to localized edge AI processing, to $50 industrial vision sensors, to 12 lines of precise Python code, and to a minimalist design philosophy that respects the unyielding laws of physics.
Less, but exponentially better.
Less, but better. The ultimate goal is restorative. We must decouple human labor from mechanical wear.
We must deploy the sensors to manage the degradation of the metal so the human workforce can return to managing strategy, problem-solving, and innovation.
Which leaves us with a final, provocative challenge for you to mull over. Take these massive industrial concepts, the calibration drift, the undocumented labor, the bloated enterprise software, and apply them to your own life, your own industry, your own daily friction.
Where are you currently acting as a human shock absorber for a fundamentally broken system?
What manual, exhausting, undocumented task are you repeating every single week simply because the foundational structure is flawed?
And more importantly, what is your version of the $50 sensor and the 12 lines of code?
What is the audacious, minimalist, first principles fix that could automate your biggest headache in 200 milliseconds?
That's the real question.
Thank you for joining us on this deep dive into the trillion-dollar blind spot of industrial automation. I encourage you to take the 48-hour protocol challenge in your own workflows this week. Find the drift, isolate the variable, and build the minimalist fix. Until next time.